Let's talk about enzymes, the tiny proteins in your body that speed up chemical reactions. Each enzyme is designed to work with a specific substrate, which is kind of like a unique key fitting a specific lock, ensuring each enzyme only performs its intended job. But how fast can the enzyme do its job? That's what enzyme kinetics is all about. Today, we're diving into a tool that scientists use to better understand enzyme speed. It's called the Lineweaver-Burk plot. It sounds complicated, but let's break it down. Imagine you're running a bar. You hire the bartender, that's your enzyme, and they have empty glasses that need to be filled. That's your substrate. At first, when there's only one glass, a low substrate concentration, the bartender fills it easily and has time to rest. But as more glasses are placed on the counter, an increasing substrate concentration, the bartender works faster to keep up. Eventually, no matter how many more glasses you add, the bartender is working as fast as humanly possible. This is the Vmax, and the Km value is how many glasses are needed for the bartender to be working at half their maximum speed. If you plot the number of glasses, the substrate concentration, versus the rate of filling, the reaction velocity, you get a curve. There's a fast increase at first, and then it levels off. This is called the Michaelis-Menten curve. Cool, but it's hard to analyze the graph and calculate Vmax because the line curves and flattens out at high substrate concentrations. So, scientists flip the data using a trick called the Lineweaver-Burk plot. Basically, they take the reciprocal of the curve equation, so you plot 1 over the reaction speed against 1 over the substrate concentration. Boom! Now it's a straight line, and it's way easier to analyze the relationship between enzyme reaction rates and substrate concentrations. To form this straight line, we use y equals mx plus b. The y is the inverse of the reaction velocity, 1 over v. The slope, m, is km over Vmax. X is the inverse of the substrate concentration, 1 over s. The y-intercept, b, is 1 over Vmax, and the x-intercept is negative 1 over km. Now, let's apply this to the previous bar example. The reaction rate, 1 over the rate of glass filling, or 1 over v, tells us how long it takes to fill a glass. The substrate concentration, 1 over the number of glasses, or 1 over s, represents how many glasses are waiting to be filled. The y-intercept, 1 over Vmax, gives us a more accurate depiction of the enzyme's top speed, or how fast the bartender can possibly fill the glasses when the demand is overwhelming. Many substrates are present. The x-intercept, negative 1 over km, measures how many glasses are needed to get to half speed capacity, and the steepness of the line, the slope, km over Vmax, visually reflects the efficiency or responsiveness of the bartender under normal demand. In other words, how the bartender, the enzyme's, efficiency drops due to different types of inhibition. A flatter slope, low km over Vmax, indicates no enzyme inhibition, so the bartender is highly efficient, even with just a few glasses. They start working quickly. The enzyme has a high affinity for the substrate. A steeper slope, a high km over Vmax, indicates competitive inhibition. It's less efficient because of interference, like a customer pretending to hand over glasses, but they're not real orders. They're just getting in the way, so the bartender is working harder to keep up. The km, the x-intercept, increases. It takes more glasses to reach half max speed because of the fake orders. The Vmax, the y-intercept, stays the same as it would with no inhibition. The bartender can still go fast, but now needs more glasses to get going. So the slope, km over Vmax, increases, so the line gets steeper. A steeper slope can also indicate non-competitive inhibition. It's less efficient even at high substrate concentrations, so it's kind of like if someone ties one of the bartender's hands behind their back. They can still pick up real glasses, but they're permanently slower, no matter how many glasses are waiting, so the bartender's drink-making efficiency drops. The Vmax, the y-intercept, decreases. Even with tons of glasses, the bartender can't go any faster. The km, the x-intercept, stays the same. The bartender still grabs glasses just as easily. So the slope, km over Vmax, increases and the line gets steeper. The Lineweaver-Burk plot and Michaelis-Menten curve are like fraternal twins. They may look different, but they have the same foundation. They both deal in enzyme kinetics. The Lineweaver-Burk plot just converts the curve into a straight line to make it easier to visualize and compare enzyme inhibition types. Let's look at a real enzyme, alcohol dehydrogenase. It's the enzyme in your liver that helps break down alcohol when you drink. But not everyone's alcohol dehydrogenase enzyme works the same way, so scientists use the Lineweaver-Burk plot to figure out how efficiently different people process alcohol. Some people have a low Km. That means the enzyme binds alcohol quickly, even when there's not much of it, so the enzyme kicks in fast and easily binds the substrate. Others have a high Km, meaning the enzyme needs more alcohol to get going, so it's slower to respond. Thus, the enzyme struggles to bind unless substrate levels are high. This can explain why some people feel the effects of alcohol faster or stronger than others. So, to wrap up, Vmax tells us how fast an enzyme can go, Km tells us how good it is at working with the substrate, and the Lineweaver-Burk plot is the shortcut scientists use to see it all clearly. Thank you for watching.